Okay, everyone. Today we have Trudi Hoogenboom, who is going to talk to us today about comparative planetology. You have the floor.
Awesome. Okay, super exciting. So I'm going to do a class today about comparative planetology, but first I'm going to talk about what exactly is planetary science, because I'm a planetary scientist and I think it's an amazing career to do, so we're going to talk about that today. So planetary science is basically the study of all things planetary, planets, moons, the processes that form them, the history of them, asteroids, comets, etc., etc. The first thing that students usually ask me is something about black holes or stars, and that's generally an astrophysicist role, but it's usually young students. Actually, even up until late high school, students will always ask me about black holes, and I'm always like, that's not something that I know a lot about. But I do know a lot about planets, and terrestrial planets and icy satellites, especially. So planetary scientists, we look at planetary rings, we look at asteroids, comets, atmospheres, all those kind of things. And we use data that is obtained generally from satellite missions, where in the past it was largely NASA that would send instrumentation on satellites to take images, collect gravity data, topography data, magnetic data, data of different wavelengths of light, just so that we could learn as much about planets as possible. These days we have sent rovers. Many of you have seen, the Mars rovers, Curiosity, Spirit, Opportunity, Phoenix, Lander, Insight, etc., etc. But what's really exciting about the last, 5-10 years is that so many other countries have their own space programs now. Japan has JAXA, the Indian Space Agency has one, Canada has one, Australia even started their own space agency in the last, couple of years. China has a space agency. And so with all those other countries coming online and learning about our solar system, combined with the amount of new space companies, commercial space companies like SpaceX, Blue Origin, Firefly, all of these other aerospace companies, Virgin, Intergalactic, all of these companies that are developing technology that with the aim that eventually we will have people on Mars, on the moon, and ideally, if you love Star Trek as much as I do, sending spacecraft outside of our solar system. So there's a couple of things that planetary scientists do that's really cool. And the first thing that I think is really cool about being a planetary scientist is we get to choose the landing sites. So we have a say in which landing sites we put our astronauts down. So for instance, the Apollo astronaut landing sites chosen by planetary scientists, all the rover landing sites chosen by planetary scientists. And we choose these locations based on the best chance of not having something fail. The last thing you want to do is build a millions and billions of dollars of instrumentation and launch it at a planet and have it smash into the ground. So we tend to find that most of the places that we have sent instrumentation, landers, rovers, all of those kind of things, any rocket landings have been on very flat landing sites. And the reason why we choose that is because we want to minimize the chance of a spacecraft coming in and smacking into a mountain or rolling down something. The only problem is that we tend to land on flat basalt, right? Because basalt, when it cools down, tends to form a flat surface. So a lot of the places we go in the solar system and where we've landed have been basalt, which is not as exciting. And so thanks to all these new commercial companies discovering new ways to land rockets safely, I think in the next 10-20 years, especially in your young lifetimes, you'll see planetary spacecraft landing on different things. So that's really cool. We also track asteroids that could be a hazard for Earth. We make maps of places in the solar system that have never been made before. We get to see places before any other human does. So I really do recommend, if you're interested in planets and space, think about it as a possible career, because it's a really cool thing to do. So today we're going to talk about comparative planetology. So I'm going to share my screen, and not my email screen, my PowerPoint screen. There we go. And it's called comparative planetology. And so what is cool about this is comparative means comparison, planetology means planets essentially, and it's the way that we compare features on on different planets. This is actually something that I grabbed off, it's one of these outreach activities that NASA has, and they call it Mars Match, but I kind of just have changed it around, to have it be more useful in an online format. So today we're going to talk about comparative planetology. And the reason we're going to talk about that is because the easiest way for us to learn about planets in the solar system, and even planets around other solar systems, so exoplanets that are orbiting around another star that we have not even gone to yet. The easiest way for us to learn about those things is when we identify features on Earth that happen to show up on other planets and moons. And one of the most obvious ones is ice caps. And so if you look here, you'll notice throughout this presentation, anything that's in a blue box will be Earth. Anything that's in a red box, like a red outline here, will be Mars. But what's really cool about this is that we have an ice cap, right? This is the ice cap of Antarctica. And it's about 3 kilometers across. It does vary depending on season. But when we came to look at the first data that came back from Mars, we were able to see ice caps as well. And so we're able to identify things that we study on Earth. And it's really easy, right? Well, it's semi-easy. It's a little bit easy for us to go to Antarctica and collect data. We're at the point where we have a lot of satellites that orbit the Earth that take a lot of information and collect data about Antarctica. So we get to learn a lot about Antarctica and ice caps on the Earth, and we use that knowledge that we have on the Earth to better understand Mars. And so these are the north and south caps of polar ice caps of Mars. The polar caps of ice of Earth are mainly made of on Earth are made of water ice, but the ones on Mars are made of solid carbon dioxide and water ice. And so polar ice caps form on any planet or in our solar system, because high latitude regions, so those at the top of the planet or at the bottom of the planet, they receive less solar energy than the equator. And so the ice caps on planets tend to be in these places, and it works on pretty much all planets and moons that we find, that the tops and the bottoms of the planets, the south and north poles of the planet, will be colder than the equator. And so it's just a really good example of how, if we go learn about our own planet, we can use that knowledge to better understand planets that we haven't gone to. And so you will notice here that the ice cap of Antarctica is about 3 kilometers across, and much larger on Mars. It's about 1,000 kilometers across. They are seasonal, and so they do change depending on Mars seasons. And you can see here's some Hubble Space Telescope images from October 1996, January 1997, and March 1997. And so in October 1996, it's a lot colder, Martian winter, and so these ice caps are making up a very large, percentage of this particular image. But as we get into warmer seasons, these ice caps, which are on Mars, are largely a mixture of solid carbon dioxide and water, begin to sublimate, and that means that they go from a solid directly to a gas and become smaller. And so there's a lot of different images you can find online. I recommend, if you're ever bored, go Google images of Mars or images of Enceladus, Europa, all of that kind of things, because all of this stuff, all of this data that NASA collects is publicly available, and so you can find it on lots of different websites. This is a Sahara dust storm. So this is the continent of Africa here, and this is a dust storm that has taken dust particles from the African continent and has transported it across the ocean. So we have very large dust storms on the Earth that do create problems for everything, right? For air travel, etc., etc. You don't see them. They don't happen regularly at this larger scale. We have dust storms all the time, all over our planet. They don't happen on this large time scale unless they're in certain seasons. But we have polar dust storms on Mars, and so you can see this red image here is this polar dust storm, this very large scale dust storm. This is a crater. These are craters here. But what's really interesting is to better understand polar dust storms on Mars, we're not at the point where we have astronauts walking across the surface of Mars. We have rovers that are still functional, working on the surface of Mars and sending data back to us on Earth. But we're not at the point, and hopefully we are at that point in my lifetime, that we have astronauts living and working on the surface of Mars. But in the meantime, the best thing that we can do is send these rovers, collect this satellite data and imagery of the planets that we're interested in, and then also better understand how these features work on Earth. Because when we understand how they work on Earth, we can better understand how they work on other bodies in our solar system. Dust storms on Mars can cover the entire planet. So you guys, when you're designing your missions and when you're getting in your teams and you're designing your engineering missions to put people on Mars, you need to take into account that dust storms on Mars can get really large and can cover the entire planet. In 2018, we have images that showed that these dust storms, one dust storm on Mars covered the entire planet. And so if you've got questions, put them in the chat, and then at the end of class, and we'll go through them all. But normally when I teach these classes, it's very interactive, but because we're recording them, definitely put your questions in chat, because this is one that usually comes up a lot. So this is a dust storm. So you have Mars here, 2018, this is probably a little bit before in 2018. You can see the polar ice caps are, roughly the same, but you can also see that this dust storm has taken over the whole planet. Dust storms can be a really large problem, or are a really large problem for electronic instrumentation. Anything any rover that we're putting on the surface of Mars, we need to protect that electronics from dust storms. It's also not a good thing for humans to breathe in. We have a very similar situation, similar but less, on the moon, where we have this lunar regolith that has very fine particles of dust, which tends to mess with instrumentation, and also isn't a good thing for humans to breathe. These things are called dust devils. So in the blue outline here, we have a dust devil on the Earth. And then we have been lucky enough through, I think it was Mars Reconnaissance Orbiter, yeah, it was Mars Reconnaissance Orbiter and the Opportunity rover, to collect images of dust devils on another planet, on Mars. And so this top image here, you can see a dust devil looking very similar to a dust devil on the Earth. And this is what it looks like from above. I grew up in Australia calling them whirly whirlies or willy willies or something like that. But in the US, we generally call them dust devils. And generally the technical term is a dust devil. But it's really interesting that we have these features on two separate planets. We have these features on two separate planets where we have very different atmospheric composition, different surface gravity on Mars, and yet we still have these features that we can identify and learn more about. These are features in the Sahara Desert over here, and we also find them on Mars. I think they're really cool because they look like the Star Trek badges, like the communicator badges when they're like beam me up, etc. They're the same shape. And so I think when people first saw these things on Mars, we were like, oh my goodness, they look like Star Trek logos, but they're not. These are dunes, sand dunes. And so we have these sand dunes all over the Earth, right? We have sand dunes. If you're ever on the beach, in areas that don't have a lot of vegetation, you'll see these sand dunes forming. But what's really cool about this is that we know the direction of wind. So even though we do not have a rover on Mars right here, we don't have a rover, we have no humans working around, we know the predominant direction of wind because of these dust created, basically sand dunes. And so whilst there's a lot like thinner atmosphere on Mars, we can still have these sand dunes forming. And so by studying sand dunes on Earth and knowing that, this is the direction, if you, actually, we can annotate on the screen. If we, this is the direction that, the wind in the Sahara Desert is moving because of the shape of these sand dunes. And we know the same thing for Mars, which is really, really cool, right? No human, no rover has ever, gone and stood next to one of these things. They're roughly the same scale, but I think it's really cool that we can learn all about these things despite, not having been there. You will notice that there is something missing from this this slide, and you'll notice it. Hopefully you notice it throughout your life in whatever classes you're attending, whether you're in middle school, high school, university. One of the first things you always want to make sure of, and I have not done that here, and it was an accident, but sometimes I think it's a really good learning moment. To better understand everything that's in the solar system, you really need to know a scale. And so you'll notice there's no scale bar here. I haven't said that these are 5 kilometers across or 2 centimeters across. You really can't tell unless someone puts a scale bar on their image. So please, when you are in your classes in middle school, high school, university, make sure you understand that. Make sure and point it out if there's no scale bar there. It's something that is really important in pretty much all the sciences, especially in geology and planetary science, but all scientific fields and engineering. So take this as a learning and always use scale bars. And this is, okay, craters. We have craters on the Earth. And we have craters on Mars, we have craters on the Moon, we have them on Venus, we have them on Mercury, we have them on exoplanets and exomoons that we have never even been to. And these are really similar looking craters, right? So despite the fact that these are on 2 separate planets, right? The blue one is Earth. This is an impact crater in Chad. And this is Lowell crater on Mars. They're similar sizes. You'll notice that they look the same, right? So you have this one crater up here is what we call a simple crater. And simple craters are really easy to identify. They pretty much just look like cereal bowls. They look like, like any bowl that you'd eat your cornflakes or Rice Krispies or Cinni Minis or whatever you're eating for breakfast. Simple craters are they look like a cereal bowl. These are complex craters that you see on the screen. And you can tell they're complex because they have stuff in the middle. And the stuff in the middle is usually, a separate ring or a different, sometimes they have central uplifts, which means they have basically a little mountain in the middle of their crater. But these are craters that look very, very similar, right? They're roughly similar sizes. One's found on Earth, one's found on Mars. And that's really kind of cool that these planets are very, very different. But we can learn so much about craters. And we have learned so much about craters, even though we have much less craters on the Earth than we do on Mars, Mercury, the Moon, etc. We can learn so much about them from the ones that we do find on Earth. Earth has a problem. Well, it's not really a problem, but Earth has this habit of destroying craters. And that is because we have plate tectonics, we have wind, we have water, we have erosion. So most bodies in the solar system, all bodies in the solar system, we assume the same cratering rate. There's generally we have a rough cratering rate. So the amount of craters that hit the Moon is roughly the same as, the Earth, Mars, etc., depending on whether your body of interest, whether you're looking at the Earth or the Moon, etc., has a thick atmosphere, because that can really, reduce the size of your craters. But it's just fascinating to me that we can learn all these things about craters on Mars just by better studying craters on Earth. If you're ever driving through Arizona, go to Meteor Crater. It's, you know, you're driving along the freeway in Arizona, there's a sign, and it's one of these things. It's an amazing thing to see. So if you're ever on a family vacation somewhere, or even when you're an adult, go see this feature, because we have, you know, there's large craters across our planet, roughly 200, I think, at last count. We find more occasionally through different data that we collect. But if you get a chance to go see a large crater on the Earth, go do it, because it's fascinating, and it's kind of world expanding just to see these, you know, massive holes in the ground that were caused by impacts into our planet. Craters are a fascinating thing to study. They're something that we're really interested in on the Moon and Mars, mostly because if you have a crater that has permanently lived in shadow, and so a part of your crater is the crater wall has created a shadow, you can have permanent ice fixtures. And so ice deposits, when we find them, are really exciting. They're really exciting for human exploration to Mars and the Moon, because they're a possible source of water, and they're also a possible source of fuel. If we're able to split hydrogen, split the hydrogen and oxygen from, you know, H2O, and separate the hydrogen and the oxygen out, then, you know, we can use it as rocket fuel as well. So there's some really exciting things to learn about craters. We have learned a ridiculous amount of stuff about craters on our own planet through nuclear tests. And that's not to say that any of the nuclear tests on our planet were created just for scientists to learn about craters. They weren't. That's not why any of these nuclear tests across our planet have happened in the last, you know, 50 or so years. But we use that information. We have used, you know, I guess there's some good that comes out of these nuclear tests, that we've used the information. We know how much energy is detonated, and it allows us to better understand craters, you know, throughout the solar system. And so this is another thing. This is a crater in Mauritania, and this is an unnamed impact crater in Arabia Terra, in the northern lowlands of Mars. And so these craters look really similar, right? They basically look like cereal bowls. You've got a bunch of simple craters here. This large crater here is a primary crater. These are primary craters too. We call secondary craters. Secondary craters are when an impact comes in, and so an impact's come in and smacked into Mars here. All of this material that was on the ground has been detonated, and then, you know, it comes out and lands all around this primary crater. And this is really, really exciting, because all of this debris lands around the crater and makes a secondary crater. So secondary craters are often really, really small, always really, really small, actually. But these are fascinating features that look very similar, even though they're on two separate planets with very different surface gravities, very different atmospheres, and almost total lack of, you know, water, especially in today on Mars. And yet these surface features are really, really similar. River deltas. These are river deltas you can find all over our planet. This is just one on the Horton River Delta in Canada, but they're all over our planet. Anywhere where you have water that is leaving, you know, coming from the mountains, flowing down the mountains, and then back out to the oceans, will create river deltas. And you can see these kind of braided streams, right? Like these. You'll have a main channel, and then a lot of little channels. And so what's super exciting is that we find these things on Mars. And when we find these things on Mars, and when we find them in other places and exoplanets around the world, around the solar system, that's super exciting, because it's, you know, evidence that that place has experienced flowing water in the past. This is Jezero crater. We have a rover driving around there right now. And we chose that location. Planetary scientists got together with the NASA engineers, chose that location only because of this delta, right? This is in a crater, but we have evidence of water. So a large channel of water coming in here. And then there's on the other side, there's not an image here, but on the other side of Jezero crater, there's an outflow channel as well. And what's really cool for that, for the reason why this whole mission was landed there, is because flowing water gives you a really, a leg up on finding life. And so we're always very interested in searching for life in any of these locations around, the solar system especially. And so if you have a large inflow of water, and then this water gets to stand in a crater, then it increases your chances of search for life. And so we currently have a rover driving around this crater, collecting data, samples, all those kind of things. Amazon River Basin Network is fascinating too, right? It's called a dendritic river channel, but you find the same thing over on Mars. And so when we find these kind of features, the very first thing we do when we get data back from a satellite on Mars is look at features that are similar. And when we find these features that are similar, it's really fun to go and figure out, okay, we know how this works on Earth. How is this working on Mars? I think it's even more exciting than when you find a feature on a planet that exists nowhere else but on that planet, because it really gives us a step up on better understanding how that planet formed, how those surface features formed. But these, you can see this is a lot of detail here. The reason why we have a lot of detail in this image and less image here is because we have so much more information taken at different scales, taken from aircraft, which is a lot closer to the Earth than, for instance, a satellite. But eventually we will have this level of data on Mars as well. We have shield volcanoes on, this is Mauna Kea in Hawaii. If you are ever in Hawaii, go see some of these volcanoes. These shield volcanoes tend to be very topographically flat and not as steep and pointy as composite volcanoes, but we see these volcanoes on Earth, and we also see volcanoes on Mars. This is Olympus Mons, largest volcano in the solar system, largest mountain too. You can see this debris lava flow field here, and then you can see this particular mountain has been hit by craters as well, right? So they had impacts hit and create craters. So not only do we have these river deltas, dust devils, ice caps, mountains, volcanoes, etc. We have all these, volcanoes that are similar on both planets. Okay, so that is we're going to stop there, and then we're going to go and do questions with anyone who has questions. We can go through the chat. Because otherwise it's set up to be more for an online thing and not for in person. Do you want to read questions? Do you want to do the thing, Nicole?
Yeah, I'll read them. Great presentation, chock full of information. Love it. Alex would like to know, how long can a dust storm on Mars last?
That's a really good question, Alex. It's a really good question. On Earth, they tend to be, they're self-limiting, right? So eventually the energy dissipates and they don't last very long. I think the longest that I've ever seen one last on the Earth is, minutes to possibly hours. I do not know how long they last, but this is an excellent question for Google. You guys are so lucky, and I know, Alex, you've been in classes with me before, so I know you're probably so sick of this, but you have the knowledge of mankind on a device. So Alex, can you do me a solid and look it up, Google it, and then put it in the chat, because every time I find something that I don't know, I go and look it up. And right now would be an inopportune time for me to do that. If I'm like, oh, everybody just wait, I'm going to go figure this out. But I really do recommend that every time you find something that you don't understand, go look it up, or ask a teacher, ask a friend, ask somebody, because it's the fastest and easiest way to grow your scientific knowledge. But then go look it up, Alex, and put it in chat, because me and I don't know. Do you know the answer to this one, Nicole?
Yes, they can last for months.
Months. Oh my
Yes,
goodness.
global dust storms can last for months. Yes.
Oh, dude. But what about like the actual dust, the little whirly, so the
The
dust?
dust devils, I don't think that lasts more than a few minutes
Yeah, that's
at
what
the
I would, yeah.
most.
Because the dust storms can last for, yeah, I think like a really, really long time, right?
Yeah,
Months and months, if not a year. But I wonder how much the whirlies last.
I think that's just a few minutes, but Alex can
Alex
Google
is going
that.
to find out and let us know.
All right. Andre would like to know, do you know how they deal with dust storms? Rather, how they construct instruments to resist dust storms? This is a big part of your project,
It's a
actually.
big part of your project. That's a really good point. The first thing you do is you want your electronics covered, and so to do that, we make sure that any wiring is fully insulated. You don't want any dust from either lunar regolith or on Mars getting into your instrumentation, into your electronics. So we tend to cover it. The only things that are not covered are features, are instruments that are taking direct measurements. And you'll notice that you'll see all this kind of insulation kind of looking covering. Some of it's thermal insulation, a lot of it is actually, but yeah, you're going to want to make sure that that does not get into your breathing apparatus too. Oh, Alex already put it there. What's the answer? What is it? Can you see?
Local dust storms, 7 to 10 days.
Yeah, but what about the dust devils, like the actual dust devils,
Yeah.
Alex? I want to know how many minutes. Oh, escape.
He wants to know also, Alex wants to know, how fine is the dust on Mars?
Very, very, very fine. Finer than the finest dust on the Earth, which is why it's so not great, which is why you want to definitely be having your 2.5 micron COVID masks on Mars. Your filtration needs to be serious.
And probably several levels of it, I'm sure.
Several levels.
Where does the wind on Mars come from? Also from Alex.
That's a really good question too. So we always say, right, you'll read books on Mars and you'll see websites on Mars that say that Mars has a much thinner atmosphere. And that is true. But wind is generated in the same way that it is generated on our own planet of Earth. What's great about Mars, though, is just there's so much fine dust to pick up and take with you. Right, and we do have that. There's parts of the Earth that are covered in fine dust, maybe not as fine on a regional scale as Mars, but it forms the same way. 25 minutes. Okay, Alex Swang says that 25 minutes is a dust devil. Yeah, that makes sense. I would have thought a little bit less, but that makes sense.
Okay, and Mata Sham, if I mispronounce your name, please correct me, would like to know, do we have an estimation of the quantity of craters? It's a very good question.
Yes, we really do. We really do. In fact, you can Google that, and that will be, I have a friend called Stuart, who's Stuart's entire career, well, no, he's done a lot of stuff, but is crater counting. He did the first crater counts on Mars, and it is a fascinating process. These days we're doing it with artificial intelligence and machine learning, but back in my day, which was not that long ago, by the way, we would collect this data, we would bring it into our GIS programs. There's a really good free program that I teach my students called JMars, where you go along and you find a crater and you go click, 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 make a circle, save it, and that program will save, how the diameter of it, whether it's oval or round, etc., etc. These days we are doing it with artificial intelligence. To varying degrees of success, but there are planetary scientists across the last 50, 60 years that literally, like, we pull the data in and we count them one by one. It's in the order of millions. The only limitation to the number of craters that we count is how the resolution of our data. Because to see the really, really small ones, you need to be flying somewhat close, to the planet. So it's on the order of millions. I have friends that have counted them. Like, it's really, really cool. But there are these great artificial intelligence codes available to you now. I had students working on this a year or two ago, because we were trying to map caves on Mars and finding them, training a AI to detect them, but they kept finding craters because they're round, and it's fascinating. But
I would
yeah,
love to go to a cave on Mars just to see what's in there. That would be amazing.
that's the first place that they're going to land, I predict.
Yeah, I think so. They can make a little
They're gonna-
habitat under there. That's what I would do.
Although I heard recently, like the Ingenuity helicopter,
Mhm.
I heard recently that they figured out the maximum weight that they can have, and then seeing can they fly like swarms of them along Valley Marinaris into
Oh,
caverns, right? Caverns or caves along. Yeah, that would be really cool in search for life.
amazing.
Really exciting.
Amazing. Just drone that whole place into
Yes.
cool caves. That would be amazing.
Yes.
Something you guys might want to think about for your project, for your research areas. Motasham also would like to know, how did Mars get the highest latitude mountains? Is there a specific reason or coincidence of nature?
No, it's not coincidental. What's really cool about, so low gravity is not good for our human bodies, right? And every one of us has evolved over millions of years, billions of years, to have our body be this shape and and work the way it does, because it's used to 9.8 meters per second of gravity. And so Mars does not have that. It has lower gravity. But what's really cool about having a low gravity environment is that you can grow your features bigger. So you'll have deeper canyons, you'll have taller volcanoes. Low gravity is exciting. And you see it in other low gravity environments as well, although not as great as Mars.
Great answer. All right, Tissia would like to know, how big are simple craters?
Simple craters really vary from, you can have simple craters that are, 5 meters across, to hundreds or thousands, not thousands, like 1,000 kilometers across. Simple craters are really, both simple and complex craters are really exciting, because not just when you're collecting data about something, no matter what it is, you want to collect as much as possible, right? So just knowing the diameter of a crater is, it's great. It's better than not knowing anything about a crater, but knowing the depth of the crater is also really exciting. And so depths of craters really do vary. You can have shallow craters, you can have very, very deep craters. They can be of the orders of meters to tens of meters to a kilometer deep, and that really depends on the surface gravity of the body that you're looking at, what it's made of, whether it's phase 2 ice or just regular terrestrial rock. But it's really exciting. It's really, my one piece of advice is, when you are looking at anything, collect as much data. You can never have too much data, in my opinion.
Yes, the more the better, especially if you're going to go to another planet.
Yeah. So true.
Angela would like to know, you talked about insulation for electrical equipment. Do you know what the best insulation material would be from the dust storms?
This is definitely Googleable, but I will tell you, Angela, I am a planetary scientist, not an engineer. So the planetary scientists go and say, so for instance, we're like, okay, we want to make a satellite mission, and we want to learn about the gravity of Mars. And so we develop a gravity instrument, and then we put whatever other instruments on the thing. Then we get together with the engineers, and the engineers say, and it's kind of a back and forth of, yeah, you can't do that, or yes, you can do that, and this is the materials we would use, etc., etc. Planetary scientists and engineers have a really interactive working relationship when it comes to NASA. Although there's a lot more engineers than planetary scientists, by the way. So if you want a niche field, go into planetary science.
Well, our next speaker, Joey, just came in from Honeybee Robotics. He might know the answer to that question.
Yeah, that's great. And you're seeing Adrian Brown tomorrow too, another great Australian planetary scientist.
Awesome. Joey, I don't know if you heard the question. We were talking about, can you hear me?
Yeah, I can hear you. Can you hear me?
Yes, we were
Okay.
talking about insulation for electrical equipment on to prevent the dust from Mars interfering. And the question was, do you know what the best insulation material would be from dust storms? And I was just wondering if you would have any ideas about that.
Sorry, what was the context there? Is that like
Dust,
a
dust storm, dust getting on the electrical equipment.
Or
yeah, so,
thermal insulation would be good to explain to.
yeah, flight hardware would typically have multiple layers of insulation protection and all that. So one of the popular choices would be PTFE coated wiring would be one potential flight choice. And then on top of that, you'd have additional layers. So yeah, there's a lot of different options depending on specifically what we're talking about hardware wise.
Okay, awesome.
Yeah.
And sorry to interrupt you, Trudy, but I
No,
thought
no,
it was a coincidence that
no,
he
this is
came
really
in
helpful.
right at that moment. All right, Tissia would like to know, what are the factors that differentiate a primary crater from a secondary crater?
Secondary craters will always have they will not look like a cereal bowl is the easiest way to explain it. Primary craters just look like bowls really nicely. And so it's to identify a secondary crater, they usually have stuff in the middle. Either they have multiple rings, or they have what we call a central uplift or a central peak, which is just created from the rebound of the surface of whatever it is, the Mars moon, surface relaxation. Eventually all craters become shallow craters, right? Because they fill in with dust and they erode. It takes millions of years. But the life of a crater is long and exciting. Well, maybe not that exciting.
Yeah. There's a lot of cool stuff that happens in craters. People underestimate those.
They do, yes.
Very much. Andre would like to know, as an expert in comparative planetology, what are your top 3 landing sites for a manned mission to Mars?
Manned mission for Mars. Okay, I'm going for something equatorial because the equator of Mars, and similar to a lot of other bodies, has a less like a more constant temperature, so less extremes to deal with. I would want to be near a cave opening, and I would also want to be near a crater or some sort of frozen water source. Frozen, some sort of something that I could somehow get water out of it. Yeah, those are my 3 things. That's a really good question, actually. Finding those 3 things is tricky though, man, like super tricky.
I agree with all of that. And I would also, if it was me, I would add, there are those little magnetic field bubbles on Mars because it doesn't have a full magnetosphere. If we could find all of those things in one of those magnetic field bubbles and study, is that magnetic field actually preventing harmful solar radiation? That would be a great thing.
That came out, there's something really recently. There's like that, any one of you can look that up on Google. There was a recent publication that actually mapped the location of those magnetic field bubbles. Yeah, that's a really great idea, actually.
So maybe that exists. Maybe one of our students will find it.
Yeah. Yeah.
And send that to NASA or SpaceX and say, land here. This is the best place.
This is a really cool idea.
Okay. Thank you, Trudi. Feel free to stay on and watch Joey's presentation. And Joey, whenever you're ready, I will do your intro.
Yeah, sure. I'm ready.
Okay. Do you want me to do your full bio? Did you, or?
No preference. Yeah, that's fine.
Okay. All right. Today we have Joey Palmowski from Honeybee Robotics. He will be talking about Redwater, a groundbreaking initiative focused on developing an in situ research utilization technology to access and extract water from below the surface of Mars. Welcome, Joey. You have the floor.
All right. Thank you so much. Let me share my slides. Let's see. Okay, can you see that okay?
Yes. Looks
And
great.
presentation good?
Yes, looks great.
Okay, great. Yeah, well, I'm really honored to be speaking. I saw the lecture lineup, and it's quite the lineup, so I'm honored to be a part of that. I wouldn't necessarily call myself early career, maybe somewhere in the middle, but I'm really excited to be talking to everyone today. So I've seen a lot of the presentations have been some kind of specific on the science side and focusing on broad topics related to, how we create sustainability on Mars. So just some background here, my company is in the business of actually building hardware for space. So we have about 50-50 split between flight projects and R&D projects. And so Redwater is obviously R&D. There's no current plans for this type of technology to fly to Mars. But the hope is that we're planning ahead now, going through a development process. These things take a long time to build out this sort of technology. And so right now it is in an R&D phase, and I'm actually leading that project. And so what I'm going to present to you today is sort of an example of how we look at the challenge of sustainability and humans on Mars, and what sort of technologies will be needed to address those challenges, and more specifically, an actual system dedicated to one of those specific tasks required. And Redwater is focused on the ISRU aspect of going to Mars. And so what is ISRU? So I imagine you may have heard that throughout the lectures, but I'll go over it. ISRU, in situ resource utilization. So essentially, we want to try to use the resources that are already on Mars. And in the case of Redwater, we're looking at specifically water, which is one of the major resources that will need to be utilized in situ. So if we look at water and what we can potentially develop from it, we can split it. We can split water. And then we can obtain two elements, oxygen and hydrogen. If we use both of those elements, we can develop rocket propellant, which obviously is going to be extremely important for leaving Mars and returning to Earth. And then if we take oxygen itself, that's also an important resource for life support, right? Because we can't breathe the environment on Mars. We do need to have oxygen for breathability. So that's one sort of side of the use of water. On the other side of things, directly using water for things such as agriculture, sustainable like farming and food obviously is going to be important. And so we're going to want to be, creating those resources on Mars. And then just general consumption. So obviously we need drinking water to survive. So that I'm sure that's a very obvious one. And then something that may not be thought about as much, just for sanitary purposes, right? For cleaning and things such as that. And then this is not a catch-all. There are potential uses for water as well, industrial related and others. But these are kind of the main ones that I wanted to touch on. And so an obvious question is, why do we care about ISRU? And there's plenty of reasons, but there's really just one reason that's kind of a full stop reason, which is an extremely cost-effective solution versus bringing resources with us. So there was a study done a while back, and this information has been presented before, but essentially you can assume that if you need 1 kilogram of rocket propellant on Mars, because of the penalty on mass, that's going to cost you 226 kilograms of rocket propellant to get it there. So you're talking about a 226 times saving to mine and create that resource on Mars. So sort of a no-brainer that we have to do it. And this is kind of the breakdown of where that number comes from. And obviously that's dominated from leaving the Earth atmosphere and overcoming gravity. And then there's also some intermediate options potentially of doing that in low Earth orbit and et cetera. But right now we're just kind of talking about how we do that on Mars. So what is Redwater? So Redwater is going to address this ISRU challenge. And more specifically, it's a system that can access subsurface ice, melt the ice, and then mine the water from the melted ice to the surface. So that requires drilling through what we're expecting is a shallow layer of Martian regolith until we access large sheets of pure ice. And I'm going to talk a little bit more about that on the next slide. But then once we reach that ice, we need to melt a little further down to create an overburden layer above us so we don't collapse. And then we can start melting and create an underground well. And then when we melt that, we're creating a water well underground, and then we can pump that water to the surface. And in a nutshell, we're utilizing coiled tube drilling, which I'm going to touch on a little more. A rod well, which is kind of the term that's coined to represent these underground wells that have been done before. And then of course, Mars. So speaking a little bit about where we would do this on Mars specifically. So you can't just go anywhere and drill into the ground and expect to access large sheets of ice on Mars. But the good news is there's some very smart people doing some great work to find places where this is going to be feasible. And I believe Dr. Than Putzig has already spoken to you. And I'm not going to try and follow his information. He's the industry leader when it comes to identifying this on Mars. But just to briefly touch on it, the obvious answer is we have to be in a location where we expect to have significant ice deposits below the surface. But then we also need to consider entry, descent, and landing, EDL. And so some important things there are going to be elevation, surface slope, and a load-bearing surface. We also need to consider that we need a source of energy. So if we're going to be doing solar, we need to be in the lower latitudes so we can use solar panels, and we're going to need a large amount of power for this system. And so work is ongoing. I believe he discussed the SWIM project, and it's been extremely important in helping us narrow into a few select locations where it becomes more and more evident that there is large sections of subsurface ice. A lot of this data is coming from MRO, which is currently orbiting around Mars with various instruments that are collecting this data for us. So now I'm going to talk a little more specifically about Redwater. So looking at a system overview, and this is sort of a futuristic concept that you see here on the left, and on the right is actually what we're building in this effort funded by NASA. And so looking at this subsystem, we of course need to store the water somewhere. So we have water storage tanks. We need compressed gas, and I'll talk a little more about why that is. We have our actual tubing for our coiled tube drilling, and I'm still going to be talking about what that is more specifically. We need some sort of mobility to get us to the exact location where we can actually reach the subsurface ice. So some sort of rover. Right now we're just baselining an athlete rover, but for our specific work, that's kind of out of scope. We're more focused on the water collection system itself. We need an injector, which I will also talk a little more in depth of, which is actually what's pushing your coiled tube and drill into the ground. A few other elements are going to be this subsurface regolith layer that I mentioned. So you're going to have to drill through rock before you can even access ice. The subsurface ice layer itself, And then you have your coiled tubing, and looking even more in depth at the subsystems of below ground are going to be an inflatable packer, which seals the borehole, and I'm going to discuss that more in detail. And then the rest of the bottom hole assembly, which is responsible for drilling and melting. And then we have the rod well, which is what we're actually creating to generate the volume of water that we need. So I've mentioned a rod well. So that's short for Rodriguez well, and that was developed by Raul Rodriguez, and he was in the U.S. Army. I believe it was in the 60s or 70s. Yeah, 60s. And the first rod well was demonstrated in Greenland in 1960s. And the way that essentially works is kind of similar to the system that I just described. So you need to access the subsurface ice first. In some of these locations, it's just a layer of firn, which is essentially packed snow. And as you get deeper and deeper, you get more compact and closer to pure ice. So you need to access that actual pure ice in order to start your well. And typically these are more complex systems because they have the luxury of doing these terrestrially or on Earth, instead of having to worry about the mass of the system that you're sending to Mars. So you can see it's a little more involved of a system here. But then once they get to that depth, they can start using a source of heat to melt that ice. And as you melt that ice, you're creating a pool of water inside of the ice. And then once that pool of water is large enough and it can sustain itself, you can actually start transferring heat while back and forth. So you pump to the surface, you heat that water, and then you circulate it back down. So you're creating sort of this closed loop system of continuously generating this well deeper and deeper. In parallel, you then also extract water out of the well, and that's the water that you're actually using. So these are actually very important in remote locations where you can't necessarily have large sources of, or for starters, you don't really want to bring in a lot of water, because similar to going to Mars, it can be very expensive to bring those things to these remote locations. So it becomes extremely beneficial to capture that resource in situ. And so the probably the most known one is the South Pole Station, and that well has been successfully producing tens of millions of liters of water for many years now. And so this is a well understood technology, and we are hoping to leverage it for Mars. At Honeybee, we've already started to do some modeling of what a rod well would look like on Mars. So of course, there's different conditions on Mars. You have a totally different atmosphere, a much lower ambient pressure, right? Your temperature is much different. And so the physics of this well are going to be quite different. And so we've developed a model using MATLAB software, and we've started to try and understand what a well would need to look like to achieve a desired throughput of water based on a daily basis. And this is sort of taking a number that seems like a good figure for what an eventual Starship launch pad may need for generating propellant on Mars. We've also done some testing to look whether or not we can actually create this well in the lab, and then also being able to take these quantitative results and validate our model with it. So that's sort of one of the first actual tests we did was using an existing Honeybee drill. And we put some heaters in the tip of the drill. We created this large ice block by fusing ice blocks together. And then we melted a well. We actually put some red dye in there, so it's a little more visible, and hence Redwater. And we were actually able to create a 90-liter well. And then from there, we could actually take the geometry of this well and make sure that the model that we created is accurately representing what that well will look like. So another subsystem that we are developing is going to be coiled tube drilling. So coiled tube drilling does have a lot of terrestrial heritage. So this is a very popular means of accessing subsurface oil reserves. So you can see in the bottom left, coiled tubing, the machines that they're using, they're trying to access 5,000 meter deep reserves, and they're trying to do it extremely quick because time is money in that industry. And so of course we're not going to need systems this large, but it is nice to know that we do have some examples that we can kind of lean on and follow and see what they've done and how we can improve. And then we of course need to shrink that for something that we can actually realistically send to space. So we are working from at least some extensive history of design and development there. We actually have already developed a system, an even smaller system than Redwater, that's called Lister. And this has been developed for a flight project. So this hardware was actually recently delivered to be integrated with a lander that's part of NASA's CLPS mission. And so pretty soon we will actually get to see this technology on the moon. And that's really exciting. And I'm going to show you kind of how that works, and because they've already built and tested this system. And so you can kind of see how that coil tubing is injected out of the top here and downward. And you can see that you can have a fairly small footprint up here for your coiled tubing to create a very long stretch of tube. And that's one of the major benefits of this technology. And so we rely on pneumatics for clearing the cuttings out. So as we go down, we're drilling through whatever it is. In this case, this is lunar regolith. When you get pretty deep, you need a good way of essentially blowing those cuttings out of the hole. And so we use pneumatic gas, and that was the pneumatic gas storage tanks that I had shown before. So you can kind of see how Lister does that here on the right. Another subsystem is going to be the bottom hole assembly. So a little different than Lister. We have a more involved bottom hole assembly. We have a heater for one at the tip to actually melt the well, but we're also drilling percussive drilling. So you can kind of see the inside of the system here and the mechanisms responsible for the rotary percussive drill. And I included two videos here showing how we've already sort of tested this size of drill pneumatically drilling. And of course, this was an early sort of breadboard test. So we're just at this stage just using simple shop air coming out of a tube and letting the drill progress as we're blowing the cuttings out. So we did limestone sort of as an example of a bit of a harder material, and then -60°C ice as well, which is closer to what we expect on Mars. Another subsystem is going to be the sealing packer. So I touched on this before. So essentially, you can ignore these bullet points. I apologize. Those did not get updated properly. But essentially, this is responsible for when you inflate this, you can actually seal the borehole below. And why that's going to be important is sort of twofold. For one, if you're not sealed, you're exposed to the Martian environment. And because of the low pressure environment, you're very close to the triple point of water. So if you're attempting to melt water, it's very possible that you would actually also begin to sublimate that water. So the water that you're planning on collecting and circulating to the surface could actually just end up vaporizing and going away. So it's important that we create at least a partially sealed environment so we can maintain a pressure high enough that we can actually melt instead of sublimate. And so that's the first sort of objective of the packer. The other one is instead of pumping, and pumps can be pretty complex, particularly for space related technologies, right? So instead, what we're doing is we're using the packer to, again, seal off that environment. But then instead of using a pump, we can actually use stored compressed gas, release that gas, and create a high enough pressure that we can actually push the water out instead of having to pump it up. And so here's a breadboard test that we did in our freezer just to kind of demonstrate how that works. So you can kind of see, you can see in this image here where we actually have the packer pressurized against the ice. And then we had a tube going through that we can then pressurize below it. And then if you have water inside there, once you pressurize that, you start pushing that water up to the surface, and then you can collect it in a containment at the surface. So now when you put all of those subsystems together, this is the concept of operations, or CONOPS, that Redwater operates on. So number one, pneumatic drilling to require depth. So kind of like I showed, where you are penetrating the ground and you're blowing those cuttings out of the ground. That's kind of step one. Once you reach the required depth, the next step is going to be to actually seal off that borehole, like the packer I had previously shown. And then you can pressurize your downhole environment so you stay above the triple point. Once you have that a downhole environment, you can begin melting, so you're actually collecting water. And then once you have a water well, you don't want to remove all that water, because the water is actually what's also helping you further melt and continuously generate additional new water. But then once you've melted enough, you can actually start extracting some of that water. And that's the last step of the CONOPS, where you again pressurize the borehole, but this time to extract the water out of the hole. So this project has been done in two phases. Phase one, we were, I'm not sure if you're familiar with NASA TRL levels, but TRL 5, it's essentially TRL 1 to, I believe 9, potentially higher. So TRL 5 is sort of when you first want to build a system that's targeting the environments of the planetary body that you're seeking to go to. And so, so in this case, we built to TRL 5, and you can kind of see the design of this system. You have the drum, the injector, and then that bottom hole assembly. We did keep this design modular because this is sort of a novel concept of, other than what Lister had done at a much smaller scale, in order to push such a large diameter tube down, there is some complexities of how that tube's going to respond to those high loads. And I'll get into that here in a minute. And then you can kind of see the additional ground support equipment required. So we have our electronics, we have our computer running the software. So this is a robotic system. And then you can actually see some of the data output to the console here. So like I said, there's many development challenges, and that's why this TRL 5 system, we made it somewhat modular. And so, you know, we were able to work through some of these challenges without having to start from scratch. And so we did experience some issues with material selection. So that's always going to be important when you're designing something for another planet. Spring back and not necessarily having an extremely straight tube, that's going to be important the deeper you're trying to go. And then something else we have to consider too is the indentations and that we're putting on the tube as we're pressing on it with this high load and pushing it downwards. So one of the first tests that we did was still sort of a breadboard test, but we wanted to actually run through the CONOPS of the pressurization and water extraction process. So this was just done on a benchtop essentially. And I'm going to kind of go through each of those steps. So first we inflate the packer. So you can see that we've now created a seal against the simulated borehole, which is just a clear tube. Then we pressurize the borehole. Okay, so now until we open a valve, we just have this water set to a high pressure. But then once we open that valve, we can actually start extracting that water to the surface. So you can see the water exiting the borehole. And then in this other video, you can see how we simulated the height of the well going through that system and then collecting in a secondary containment. And then once we sort of proved that the concept there, we were able to finish assembling the final version. And the first test we conducted was an end-to-end freezer test. So there's a video here kind of showing once we reached the depth required, we were actually able to start melting the well. And we did, again, pour red dye in so you could actually visualize that well. And you can see that we had a successful test here, actually generating that well and also collecting the water. Additionally, we we tested in TVAC, which is a thermal vacuum chamber. And so this is critical to advancing your technology to a point where it can be considered a high enough fidelity for a flight mission. So TRL-5, you don't necessarily need to be TVAC ready, but this was important in sort of establishing a baseline for the technology that will be important moving forward. And so we did also have a successful TVAC test. It's a little harder to get video of that, and particularly we had to use an actual containment for the ice, but we were able to cut that in half afterwards, and you can actually see the well that we created. So another similar successful result in TVAC. You can kind of see the data that we collected here. And that was again in -70 to -50 C ice, which is what we expect on Mars. And we tried our best to maintain a pressure as close to the Martian environment as possible. That should be around 5 torr or so. So you can see that we kept it around below 8. It can be kind of difficult when you're actually pumping gas into this chamber to also continuously remove it at the rate required. So then we moved into our phase 2 design, and then this is a TRL-6 design. So more commonly, you would see a TVAC test in order to validate your TRL-6 design. So we kind of jumped the gun on that. Never a bad thing to be ahead, but this was more so an effort to take our lessons learned from the previous phase and also create a system that's no longer modular and really packages this more in a flight-like fashion, trying to reduce mass and volume. So you can kind of see each of the subsystems here and how those were redesigned. The drum and the coil tubing here, you have the injector system, and then each of the subsystems of the bottom hole assembly, including the packer. So part of that phase 2 development, we needed to ensure that without the modular system, we would be getting a straight tube every time. And so we went through and make sure we fully understood the geometry and the configuration of our injector rollers that would generate a straight tube. And then once we did that, we incorporated that into this TRL-6 design, and this is where we landed. And you can kind of see some of the test articles of generating those straight tubes. We also did some improvements on our heated auger, so just creating a more uniform heated surface, and we were able to test and validate the heated surface using a FLIR thermal IR camera, as you can see here. And then we also made improvements on the sealing packer. So previously we had chosen a material that's not able to meet all of the requirements for an actual mission to Mars. So instead we looked at heritage materials, and we landed on a material that was previously used in the airbags of past Mars missions. And so this system, or this new material, has been already tested at the temperatures expected in the Mars-like conditions, and we were able to confirm that this is a valid design as well. And right now we're actually finalizing the phase 2 assembly, and you can see some of the progress. So we're able to roll these coiled tubings just on an off-the-shelf tube roller here, as you can see, and we actually insert our bundle of wires and tubings afterwards. So this is all the electronics, your motors and your heaters and all that down at the bottom hole assembly. Those wires have to travel through that coiled tubing, along with the tubes responsible for the compressed gas. So you can kind of see all of that pre-rolling that too. You can kind of see the assembly progress on the drum and injector here. We did a test run of straightening the tube, and as expected, and we were happy to see that we were generating a straight tube. Finalized the bottom hole assembly. We confirmed that the packer was inflating correctly, and then we kind of put everything together on the bench top and just did some final checkouts. And so now we're preparing for our final end-to-end phase 2 test. And so when we look at our robotic ConOps, this is what we are hoping to do in our test facility. So we're first going to need to calibrate the systems and make sure that the motors are functioning properly. Then we do something called seep, which is we start to move our drill to the surface, and then we can actually figure out where that surface is before we go full power on the drill. Once we've identified the top surface is when we would actually start our drilling operation. Once we drill to the correct depth, we need to prime the well. So as discussed, we would inflate the packer, generate a high enough atmospheric pressure downhole, and then we can actually start generating the water. So then we can melt our well. And then once we've melted enough water, we can begin to extract some of it. This is our phase 2 test plan. So since we've already validated in TVAC, we've elected to run this test in our freezer instead. That gives us the ability to use these clear ice blocks so we can better capture the test and get good video of that. So you can kind of see it's a fairly complex setup inside of the freezer. And this is the setup from phase 1, but it'll look very similar for phase 2. And then this is from the model, this is the well that we hope to generate. So from this testing, we can take the generated well and try to validate the model that we have. So beyond this end-to-end test, that'll essentially close out the NASA-funded project. But the hope is that we would continue to work on further developing Redwater. So one of the major next steps would likely be an analog location to actually test this hardware in an actual ice sheet. So these images are of a field deployment that I was a part of in 2019, where we went to Greenland and we tested one of our deep drilling systems. This is a wireline drill, so a little different than the Redwater technology, but not so different that you can't also envision the technology being tested in a similar location. So this is a critical next step into further understanding and validating this technology before we can actually do the final development phase of envisioning sending this to Mars. We've done various types of outreach throughout this project. So one of those is through RASCAL. So I'm not sure if you've heard of RASCAL, but it's something that colleges can submit. It's essentially a competition, and a team can submit a proposal, and then you, if you're selected as a finalist, you can present your technology or your system level design. And so this was actually the 2023 recently happened. This is 2022 RASCAL, and actually the number 1 and number 2, first place and second place teams utilized the Redwater technology. And so that was pretty cool to see that it was the judges liked them choosing that technology. And the team here, University of Illinois, actually made a really cool animation / video game of how a Redwater system would look. And so I'm going to play that video for you just to give you an idea of down the line what this fully envisioned system could look like. So they chose to go with a stationary system instead of on a rover with mobility. But you can see it's quite a lot of ground support operations required, which have been out of scope for Honeybee's phase of work, but are going to be extremely important to envisioning the system as a whole. So as you can see, Redwater was not the only aspect. This was a large scale or a high level architecture that they presented. And so I thought that was pretty cool. And then they even did a pretty cool, almost like a video game where you could control an astronaut walking around the location there. So really cool. We are also working on some spin-off technologies. So this would be another system designed for Mars, but more so focused on science. So Redwater is more focused on resources and collecting the required resources for sustainability, whereas the other side of things would be actually trying to determine if we can find life on Mars, right? And so you can envision a similar drill needed to access the subsurface, but then instead of collecting water, you have downhole instruments that are performing the science. And similarly, you can have a very similar system on the moon, right? So we talked about Lister, but we call this one Rebels, and it's essentially the scaled up version of Lister, but it's also more capable with a drill as well. And so we're looking at anywhere between 10 to 100 meter deep access on these drills. And so I'm pretty excited about the future of this technology, and I hope that you can get some motivation from it, and yeah, maybe feel free to borrow some of these ideas and concepts, and definitely reach out if you have any questions, want to know more about the technology. I'm an open book, so thank you very much.
Wonderful presentation. Thank you, Joey. I have some questions. When you were talking about going to Greenland, did you actually completely test the technology, or were you just scouting the area?
We actually tested the deep drill technology. So this, like I said, this is different than Redwater, but in a way fairly similar. It also has a bottom hole assembly, but instead of being on a rigid coiled tube that's injected, this was a more of a loose passive wireline system. So it's lowered down, and then it uses an anchoring system to actually inchworm, and that's how you actually traverse downwards instead of pushing from the surface. And so you can kind of see where we set up the drill here, this platform, and then what you can't see is the hole under this cover here.
Okay, one of our students, Ahmed, I believe, has a question. If you want to unmute yourself, or you can type it in the chat.
Okay, hello, can you hear me?
Yes.
Yes, I have a question. Mr. You said that we use water to generate rocket fuel. That's right, right?
I'm sorry, what was the last? Yeah, so indirectly you're using water, right? So you take oxygen and then hydrogen, and then you can process rocket fuel from there, right? So it's not a direct process. I sort of oversimplified that, but the overarching resource that's gonna enable the ability to create in situ rocket propellant is gonna be the water.
Yes, the water. But my question is, like, when you spread the hydrogen and oxygen, we have like in a gas, we should to go convert it to like liquid, and when we want to convert, we need a pressure, right, to convert the gas, like liquid hydrogen to liquid hydrogen. We need the pressure, like that means we need the factories to convert for this convert, right?
Yeah, absolutely. So as far as the Redwater system itself, what we are considering in scope is collecting the water within a tank and then delivering that water to the next step of that process, right? So that additional phase of processing to actually get the liquid propellants is sort of out of scope for Redwater, but absolutely that's going to be an important part. And there's a lot of other NASA funding focused more specifically on that type of work.
Okay, thank you.
Yeah.
Okay, and for our budding engineers in the audience, why do you have to do so many tests on all of this? Why do you have to test and retest and test and retest?
Yeah, no, that's a great question. So obviously, if anything's going to fail, you want it to fail in a test. These missions can be very expensive, and I don't even know if we've ever funded a mission quite as expensive as something like this endeavor would cost. Even Redwater itself would be upwards of one of the more expensive missions we've ever conducted, right? So you obviously don't want to have any failures throughout that mission. So you test everything you possibly can and as close to an environment as you're expecting to make sure that you've accounted for everything. Of course, you want to do the design and analysis effort as well, but some things are you know, better validated with actual quantitative data and you know, putting it to the test. So we do a lot of you know, thermal testing in our freezer. We do TVAC testing, as I've shown, in various vacuum chambers, and so it's definitely very critical. And any technology you've ever seen flown has been tested many times. And I can tell you that Honeybee sending a drill to the moon within a year or two on another CLIPS mission, and I know that that particular drill has been tweaked and tested for over a decade now. So these are long-term efforts to get reliable technology that you can trust sending to Mars.
And final question, great answer. Will the atmospheric pressure make a difference with your drilling system? Oh, and then there's one more question that just came in.
So as I stated before, there is a factor to consider when you melt the water, because you do need to consider the triple point of water, where instead of staying in the liquid state, you could actually end up sublimating, or you could either vaporize the water that you created, or your ice will just directly sublimate. And so from that perspective, it's very important. Another perspective is the delta pressure from the outside environment versus the pressure that you're using to eject your cuttings out of the hole. So that's critical as well. Heat transfer is an important one. So when your environment is a lower pressure, you're not going to dissipate your heat as well. So you have to be very careful that you're properly duty cycling and cooling your equipment so you're not overheating and damaging anything. So there's definitely some things to consider. Yeah.
And from Tissia on the same subject, for extraction of water, instead of increasing or decreasing pressure, can the tube just suction the water out like a vacuum cleaner?
Yeah, so the delta P itself would not be large enough to create that type of suction. Another design variant could be baselining a pumping system. And that's sort of where we originally tried to take Redwater, but pumps can be fairly complex, and also you have to, like, anytime you're considering moving components, you have to factor in wear rate and potentially degradation of that performance over time. And so to simplify and make it more likely that the technology is robust for Mars, we felt like the positive pressure solution is a better route to go until at least flight pumps are more further developed. And we do think that technology will continue to improve as more and more things are, you know, being tested in space. But right now it was hard to identify a pumping system that we could trust for flight.
Okay, wonderful presentation. Thank you so much, Joey. It's really appreciated. It will be uploaded. Oh, one more question. What would be the approximate cost if we incorporate Redwater into the Mars mission?
That's a good question. I can tell you it will likely be the overall mission of sustaining a water, or let's say a propellant plant on Mars, is most likely a multi-billion-dollar endeavor. Redwater itself is going to be in the tens of millions of dollars, I'm sure. I can't tell you for sure, and I prefer not to even think about that side of things. I just like working on the technology, because that's typically what's the showstopper, right? Is how much it's going to cost. But it'll be a very expensive endeavor. But we're doing everything we can to you know, to help minimize that.
Oh, yes, of course. It's always about the money, right? Thank you so very much. Your video will be uploaded within the next 24 to 48 hours if you'd like to share it with anyone. Great job. Very informative, very important information for these students and for the public to understand. Thank you so much, Joey.
Yeah, thank you for having me. And if anyone has any further questions, please feel free to reach out. If the slides are posted, you can get my email from the last slide. So
Okay, and they can also email me if they don't remember that. I can send it.
all right, good luck, everyone. Bye.
Thank you. And students, at 1:30 Pacific time, so 2 hours from right now, Dr. Madhu Thangvalu will be speaking to us. And so if anybody, Joey, you can feel free to join. Anybody else? I will be here on the same Zoom link in 2 hours for our final speaker for today. So I will see you all later this afternoon. Bye.